on to the polyprotic acids. Polyprotic acids has more than one proton, and each time one of these protons leaves, it gives its own Ka. The first one leaving is Ka1, the second one leaving is Ka2, third one is Ka3. This is going to be the greatest value of Ka, this one will be smaller, this one will be smaller yet. So the value of the Ka is going to get smaller and smaller and smaller. Ka2, Ka3 usually, not very often for Ka4 and beyond. The exception to this polyprotic rule, H2SO4. There is the exception. There's no equilibrium for the first. So Ka1 isn't given. It's a strong acid. So you only deal with Ka2 or the second ionization that's going on. For example, and I'm going to write down the problems down below. For example, and this is one of the objectives, you have 0.1 molar phosphoric acid. Ka1 is made up to be 1 times 10 to the negative fifth, Ka2, 1 times 10 to the negative seventh, Ka3, 1 times 10 to the negative 10th. Find, among other things, the hydrogen ion concentration or the hydronium ion concentration, the pH, concentration of the H2PO4 1-, the concentration of the HPO4 2-, and the concentration of the phosphate. Okay? First one is no big deal. It's what we've been doing all along. Let's just jump in with this because it's the strongest base or acid, strongest acid present. So you got 1 times 10 to the negative fifth equals x squared over 0.1. This x squared is going to be H plus and H2PO4. I'm going to write down that equation down here so you can see. H3PO4 plus H2O liquid, H3O plus H2PO4 1-. This is X and this is X. So in this equation up here, the X squared is both the hydronium and the dihydrogen phosphate ions. Cross multiply, x squared equals 1 times 10 to the negative 6 square root. X equals 1 times 10 to the negative 3. That is equal to the hydronium ion concentration, and that is also equal to the dihydrogen phosphate ion concentration. The pH is a negative log of that, so the pH is 3. The next equation for the second ionization, you're starting with this stuff. H2PO4 minus plus water, liquid, equilibrium, gives you H3O plus HPO4 2 minus. Okay? Now, you cannot use x squared because this number is going to be different from this number because it's like with the water and like with a mixture of two acids, and this is a mixture of two acids. This is going to be given to you up here, 1 times 10 to the negative third. So here we really do have to write things out. So for the second ionization, 1 times 10 to the negative 7th equals the hydronium ion concentration times the HPO4 2 minus divided by the dihydrophosphate. Plug in the numbers. 1 times 10 to the negative 7, 1 times 10 to the negative 3, not x, because it's already given to you from here, times the unknown, the HPO4 2 minus, divided by this number, which is also 1 times 10 to the negative 3. Well, look at that. Those two terms cancels. So the hydrogen phosphate is equal to 1 times 10 to the negative 7. Except for H2SO4, H2SO4, the concentration of the anion with a negative 2 charge will always be Ka sub 2. Always. Because that and that will cancel out. That and that will cancel out. Always. Because that's X and that's X. So that's a shortcut for you. We're not done yet. The hydrogen phosphate ion can now finally react with water, liquid, to form equilibrium. H3O plus PO4 3 minus. This, again, is what we had before. So now we got to plug it in to the Ka expression. Ka H3O plus PO4 phosphate over hydrogen phosphate. Now when we plug those numbers in, they're all different, and you actually got to pull out the calculator. 1 times 10 to the negative 10 is Ka3 equals Ka3 equals 1 times 10 to the negative 3, which is from up here, times the phosphate over 1 times 10 to the negative 7. Cross multiply, solve. 1 times 10 to the negative 14th equals the phosphate ion concentration. It's a lot of work, but just keep your eye on the ball and make sure you don't assume the x squared beyond the first ionization energy. After the first ionization energy, you cannot assume x squared. You got to go with the log form. That's one. That concludes this lesson on bases and polyprotic acids.